Having looked at unconfined aquifers, we turn now our attention to confined aquifers. These form when waters infiltrate the ground in a recharge zone, enter a non-horizontal permeable layer, which is bounded by impermeable lithologies and which plunges into the ground steeper than the topography. As a consequence, water will flow along the deepening layer and eventually form an aquifer, which, beside in the recharge area, is fully disconnected from the surface. Eventually, water can reach discharge areas, such as some rivers, or be pushed to move upward through the nearly impermeable layers as shown in the slide. In the slide, you see now associated water table which forms the upper boundary of the unconfined aquifer, and we'll drill into it. Now, you can also see the confined aquifer. A well targeting the deeper confined aquifer will traverse the low permeability aquitard and eventually reach the aquifer. At this moment, something unexpected occurs, namely that the water in the well will rise far above the top of the aquifer itself. These are called artesian wells. Clearly, a behavior very different from that of the unconfined aquifers. This shows that the confined aquifer is under pressure and that it has a strong hydraulic head. In some cases, water might even come at the surface, forming a kind of fountain. In the latter case, we speak of a free-flowing spring. Connecting the piezometric levels in the different wells, one defines a potentiometric surface. As you can see in the example in the figure, this surface can be above the ground. Including the same kind of measurements for a region, you can build a map of the potentiometric surface. This is a key document to predict flow patterns in the deep underground. To further discuss key phenomena associated with confined aquifers, we will make the example of the Dakota aquifer, one of the largest aquifers of the world. A schematic and vertically exaggerated geological section is shown now in the slide. Note that the Dakota sandstone outcropping in the Black Hills, dipping to the west and flattening the central part of the basin. Sands are sandwiched between less permeable layers of shales and other Paleozoic rocks. The recharge region of the aquifer, we said, is the Black Hills in the west of South Dakota. Here, waters infiltrate the ground and follow a few major aquifers composed of porous sands. These aquifers are continuous for hundreds of kilometers and lie at depths of hundreds of meters in the east of the state. Agriculture is of great importance in South Dakota and in most of the central US, and a huge amount of waters have been pumped for irrigation. The consequences are clearly seen when comparing the potentiometric surface in 1909, for instance, with that of 1940, when the water table was at places hundreds of feet lower than at the beginning of the century. The lowering is obvious and has sparked large discussions and worries on how to better manage the badly needed water resources. Note also that because water flow is slow, stopping does not lead to an immediate improvement of the situation, and substantial time will be needed to return to a substantial, sustainable level. Similarly to, and probably more than what we have seen for unconfined aquifers, further important consequences of overpumping is land subsidence. When the sands of the aquifer are water saturated, the water exerts a pressure on the grains, which keeps them somewhat at distance from each other. When water is extracted, then the grains will move to a better compaction, producing land subsidence at the surface. As you can see from the measurement on the pole, water in the agricultural region of the San Joaquin Valley has descended by tens of feet within 50 years as a consequence of over-extraction. Confined aquifers are great opportunities because of the large amount of water they host and because contained waters are often of good quality. There are, however, challenges, some of which have already been mentioned. In the next clip, we expand these topics.